Okay, so welcome to day 10, and we're going to talk about fats, oils, and emulsifiers. This is another big category of ingredients used in baking and pastry. Obviously, we use some form of fat, oil, or emulsifier in a lot of different baked products. And the reason why, of course, is that they add a lot of flavor, they add a lot of tenderness. There's a lot of good things about fats and oils. So there are a lot of terms in this chapter um, of the textbook, and you can see some of the keywords that are used throughout the chapter. But I'm going to bring your attention to some of the big ones. Just the first one, lipids. Anytime you see the word lipid, that just means it's some form of oil. Um, there are tropical oils, emulsifiers. Emulsifiers are things that help bring oils and liquids together and play nice together. Um, there are a lot of rather technical terms in this chapter regarding oils and fats, like triglycerides, fatty acids, saturated, monounsaturated, and polyunsaturated fats, omega-3 fatty acids, trans fatty acids. Um, there are a lot of different aspects of fats, and we should know as much as we can about them so that we know how we can use them. We'll go into them in a little bit more detail in a little while. Um, Hydrogenation is something that we'll talk about. That's the process of turning a liquid fat into a solid fat. Beta prime crystals are something that we'll talk about too. Beta prime crystals are dealing with chocolate, so for primarily, but basically beta prime crystals exist in all fats. Um, and then we'll get into some of these other things that you see here when it regards lard, different types of fats, different types of shortenings and oils, so that we can better understand what the ingredients are we're working with. And remember, some of these products are not readily available in the supermarket. Some of these things are strictly for commercial purposes, and for all of us who are uh, aspiring to work in the commercial business, you'll want to get to know about these commercial products. So fats, oils, and emulsifiers are important moisteners and tenderizers. Fat generally will tenderize through shortening gluten. And what it does essentially is it makes it difficult for gluten to form because it gets in the way. It makes it difficult for the proteins in gluten. We've talked about gluten and gliadin. It makes it difficult for them to connect and form gluten. This is why we call shortening, because it shortens the gluten. Fats are also important for tenderizing and moistening. They hold moisture when they're emulsified with moisture, but they do have health implications. After all, we don't want to have too much fat in our diet, but a little bit of fat in your diet is necessary, and it's good for you. As bakers, we should understand these things. We should understand these fats and how to use them and how to substitute them, and to know what fat to choose if we're writing a recipe from scratch. Because after all, it's one thing to just spend a whole career following someone else's recipes, but eventually you're going to want to form your own. Okay, so generally, all lipids, whether they be oils, hard fats, doesn't really matter. They do not dissolve in water. And this includes things like flavor oils and essential oils. They don't dissolve in water. They can be mixed with water, but generally they will always separate out from water. And the only thing that can help bring them together is an emulsifier. Emulsifiers are different substances, as I say, that help oils and water or oils and liquids play nice together. Generally, as a general rule, when we say the word fat, we're generally talking about things that are at solid at room temperature. So that includes lard, shortening, certain tropical oils. These are things that are solid at room temperature. Butter is also the same way. It remains solid at room temperature. They sometimes referred to as lipid or solid or liquid, but the reality is that, and I use the word fat interchangeably. I just refer to all oils and fats as fat, but the reality is that we can separate them out. Their chemistry varies a lot, and you can see in this chart based on their composition, what they're made of. and how the fats are balanced can vary a lot depending on the source of the oil. For example, at the top of the list is coconut oil, which is high in saturated fat, 91%. Whereas you get down to the bottom of the scale and you can see canola oil is very low in saturated fat. So the composition of the oil can have a big effect not only on the health effects of the oil or fat that you're using, but also can have effect on the flavor. Coconut oil has a distinct flavor, olive oil has a distinct flavor, butter certainly has a distinct flavor, and it's a matter of choosing as a baker whether that flavor and those qualities are something you want in your baked product or whether you'd like to try something else. Generally in baking, most of the fats we use are hard fats, most of them. We do use some oils in certain cake recipes, muffin recipes, and so forth, but generally oils, liquid oils, aren't used nearly as often as hard fats are. So let's talk about oil. Oil is liquid at room temperature. It's typically from vegetable sources, soybean, canola, corn oil, for example. Typically, tropical oils are solid at room temperature, but they melt quickly at room temperature. So you think of like the tropical oils being in the tropics, coconut oil, palm kernel oil, generally are referred to as an oil because in those climates, if you were living down there and you had some of those oils, they would be liquid because it's so warm outside. They generally have a low melting point. But in cooler environments, they remain solid, and especially if they're cold. So all fats and oils are triglycerides. And what that essentially means is that from a chemical point of view, that they have a glycerol and fatty acids connect to them. And a triglyceride consists of 3 fatty acids attached to a glycerol molecule. And what that essentially comes down to is that it's just a way of differentiating this type of fat, a triglyceride, from other forms of glycerides. As a baker, we really don't need to worry too much about that as much as we need to understand the quality of the fat that we're using. But it's good to understand what's going on. An emulsifier can be liquid or solid. So one important function of any emulsifier is that it will allow a stable mixture of 2 or more ingredients to mix when they ordinarily would not mix. So oil and water, for example, cannot ordinarily mix. Add some emulsifier like lecithin, for example, as mentioned down here in the examples, and lecithin will help the oil and water combine and hold a stable mixture. So in an emulsifier, part of the molecule is connected easily to water and the other is attracted to oil. And what that does, it allows little globules of oil and water to connect and hold together as a stable mixture. That's very important to us because we use emulsions all the time. Lecithin is a very common one that we use as far as an emulsifier because lecithin is in eggs. But in a factory environment, mono and diglycerides you'll see listed a lot on different ingredient labels, and those are commercial chemicals, basically, or they're compounds that allow an emulsion to take place. So there are different types of fatty acids, as I mentioned. Triglyceride is generally the most common, but then there are diglycerides and monoglycerides, and this just helps, it helps to understand that there are different types. A fatty acid generally is part of the molecule that's attracted to fats and oils, while the rest of the molecule is attracted to water. So one is lipophilic, the other is hydrophilic. And what that just generally means is that the one component will attract itself to water, one will attract itself to oil. A fatty acid is part of the makeup of fats and oils, and it can be short or long. So some are referred to as long fatty acids, short fatty acids, saturated or unsaturated fatty acids, trans fatty acids or not trans fatty acids, and then there's the type of fatty acids that are referred to as an omega-3, omega-6, or omega-9. What does that mean? Well, when we get into fatty acids, a saturated fat is one that is long and straight, like you see here at the bottom illustration. And what that means essentially is that it's saturated with hydrogen. So there's tons and tons of hydrogen here. All these H's are hydrogens, and it also is a straight line. It has no breaks in it, which means that it doesn't break up easily. Saturated fats, from a health point of view, from a nutritional point of view, are harder to digest, and generally when we do digest them, they're strong enough to make it into our bloodstream and attach themselves to our arteries, which can lead to coronary artery disease. Unsaturated fats, on the other hand, have weaknesses. They have a bond that is not as strong, and that breaks up easily into smaller, shorter chains and easier to digest components. So we can see a double bond here between the carbon atoms. The molecule is not straight in an unsaturated fatty acid. So a monounsaturated fatty acid has one weak bond, and that makes it easier for it to break up. Then we can see a polyunsaturated fat has several weak bonds. And you can imagine that a polyunsaturated fat is very good for you in many ways because the components break up easier, making it easier to digest, and we can actually extract a lot of the nutrition out of the fat when something is polyunsaturated. Now, what it means by an omega-3. See, an omega-3 fatty acid has the last double bond 3 carbon atoms in from the end. So you can see down here on the right, 1, 2, 3 hydrogens, and then there's a double bond. What that means then is that it has just 3 hydrogens before the double bond. An omega-6 would have 6, an omega-9 would have 9. So from a nutritional point of view, omega-3, omega-6, and omega-9 fatty acids are thought to be very good for you. You'll find them a lot in salmon. You'll find them a lot in certain vegetables. They're a necessary part of your diet according to nutritionists and dietitians. And if you eat a diet rich in omega-3s and omega-6s, you will most likely have a healthier relationship with fats than someone, let's say, who's eating all saturated fat. Now, then there's trans fatty acids. And trans fatty acids have gotten a real bad name lately because what happens here is in trans fatty acids, it has a double bond, but it's been flipped. And you can see in the illustration where the hydrogens have been flipped to the other side. These are present in butter and partially hydrogenated fats, like partially hydrogenated shortening. It's thought to be, trans fatty acids are thought to be very bad for you, especially if you have a diet that's heavy in trans fatty acid. Trans fatty acids typically are common in deep fried foods because a lot of deep fry oil that is used in a lot of commercial environments especially are made with partially hydrogenated shortening, which means it's high in trans fatty acids, and then the food is high in partially hydrogenated oil and trans fatty acids as well. So why is it bad for you? Well, the thought is that what's happening with trans fatty acids is that they will increase your LDL cholesterol, your low density cholesterol, and decrease your high density cholesterol, which means then you're going to have a higher risk of coronary heart disease. This doesn't happen overnight, obviously. It's something that takes place over a lifetime of eating habits. But, if you're in your 20s now is a good time to start thinking about how much trans fatty acid you take in so that when you're 70, you're not regretting that you had a diet that was rich in trans fatty acids. Then there's mixed triglycerides, contain a mix of fatty acids, short, long, saturated, unsaturated. It's a common type of triglycerides in foods, and it represents this illustration is just a simplified representation of a mixed triglyceride. But Who worries about this kind of thing? Well, there are people out there who work for companies that make oils, that make fats, make shortening, for example. And the kind of fats that go into these products really matter to them because this is their life's work. Mostly chemists and food scientists who are very concerned about the kind of fat that's being put into something so that what reads on the nutritional label will attract customers to buy foods that they're producing. As a baker, it's good for us to understand them. So if we do get that hard question from a customer and somebody says, so tell me about, the nutrition of this product that you're making, you're able to answer intelligently about what kind of foods, what kind of fats are in this product and how healthy or not so healthy they are. It'd be better to be able to explain it in an intelligent way than to not have any idea what's in your food that you're serving. So this is why we study this. So the fatty acid profile. Each fat contains a distinct mix of fatty acids. The higher it is in saturated fats, the more solid the fat is. And it also means that it has a higher melting point. So shortening, for example, has a much higher melting point than butter. Butter has a melting point of about 88 degrees Fahrenheit. Shortening is about 100 to 105 degrees Fahrenheit. Why does that matter? Well, with a higher melting point, that means that it's going to remain solid longer in the oven while baking, which means that you're going to probably get better volume out of your product. So your product's going to puff more. It's going to have possibly a better appearance, and that will lead to a more attractive product that will most likely sell better. Animal fats, tropical oils, and cocoa butter are high in saturated fatty acids. So, eating a lot of chocolate in your diet, for example, you're taking in a lot of fat. The fat that's in chocolate, for example, cocoa butter, usually starts melting at about 91 degrees Fahrenheit, a little bit higher than butter. It's recommended by the FDA to keep the saturated fats in your diet down to a modest amount or a moderate amount. They always stress moderation. Again, this isn't a nutrition class, but at the same time, when you're talking about fats, it's good to have at least some conversation about it. The higher a fat is in polyunsaturated fats, the more likely it is a liquid at room temperature. So a lot of oils that we consume, things like corn oil, soybean oil, and so forth, they have some monounsaturated fat in them, but they also have some level of polyunsaturated fat. And the more polyunsaturated fats there are, the more likely it is to be a liquid fat or a liquid oil. Most vegetable oils are high in unsaturated fats, and there are certain oils that are considered to be more healthy than others. Now, solid fats contain many tiny crystals of fat. Now, we think of crystals and we think of salt crystals, sugar crystals, but fat also crystallizes. And they're highly ordered arrangements of molecules bonded to one another. They're so tiny that most fats feel creamy smooth, but yet that's because in the mouth they're melting as a result of the heat in your mouth. These fat crystals are what make solid fats stay solid. So like in butter, butter is crystallized, fully crystallized when it's in the refrigerator. But when you pull it out and leave it out at room temperature, it starts to soften. What's happening there is it has two main crystals in butter. One of the crystals starts melting at room temperature. The other crystal remains solid at room temperature. So the butter gets soft, but it doesn't fully melt at room temperature. It takes a little more heat to get that second crystal to start to break down and start to melt. Generally, solid fats are high in saturated fatty acids, especially long ones, and that makes them stronger, makes them a little bit less digestible, but it also makes them a little bit more dangerous for your health. So this is a little description about the fat crystals in solid fats. One of the most resilient ones is in chocolate. Chocolate has 6 different crystals in it, very complex fatty acid or fat crystalline structure, and each one of those crystals melts at a different temperature. When it comes to chocolate, if you're just grabbing a chocolate bar at room temperature, some of the crystals have already started melting. Um, and as your hand touches the chocolate, the warmth of your hand will start to melt other crystals. So you'll find that chocolate generally, if it's properly handled, it will start to melt when it gets above 91 degrees, and your hand is generally above 91 degrees. So fats are rather, as I say, rather complex, and they form a very complex structure. Now, we refer to as plastic fats. Some people, I've even heard rumors, some people saying, well, eating shortening is like eating plastic. Well, that's actually a rather ignorant way of looking at things. It's just a sign of ignorance. Somebody doesn't understand how it works. When we say plastic, we're not talking about plastic as in a plastic container. We're talking about plastic as in soft and moldable. When something is referred to as plastic, it's malleable. So generally, something that is plastic, let's say butter, for example, is not very plastic at refrigerated temperature. But as it gets warmed up to room temperature, it becomes more plastic. It becomes more malleable, more bendable, more moldable. So what is going on there then is you have a little bit of liquid oil trapped in a network of solid fat crystals. So it does become more malleable. Now, all-purpose shortening, lard, butter, they all have different levels of plasticity and different levels of moldability. Shortening, for example, you can throw in the freezer and it'll still remain pretty plastic. It remains rather malleable, even at cold temperatures. Part of the reason why is because there's always some of the fat in shortening that's crystallized and some of it is liquid. So it's very temperature dependent. When it's in its plastic range and it's in its temperature range where it's most malleable, it's easier to cream, spread, pipe, roll, laminate, etc. We can use it for a lot of things when it's in that state. When butter first comes out of the refrigerator, it's not plastic much at all, so it's very difficult to mold it until it starts to warm up. So the main steps in processing fats and oils include extraction, which is like pressing of seeds, or in the case like soybeans, pressing them for extraction. Olives, for example, are pressed to extract oils. There's also refining. That refining process then is a matter of removing impurities and removing any sort of odors or aromas that are not desirable, and any other sort of compounds that might be in the oils that would cause bitterness or any other undesirable traits. To increase functionality, there's also hydrogenation, where they blast the oil with hydrogen and heat under high pressure, and it will change the structure of fat and turn it from a liquid into a solid. You can aerate it, where you pump air into it. There's a lot of different methods that can be used. Even interesterification, which essentially is changing the physical structure of the oil so the body doesn't recognize it, and then it doesn't enter the bloodstream. Most bake shop fats are more highly refined than what you'll find in the supermarkets. They're composed of almost 100% pure triglycerides with everything else removed. The exceptions to those are more natural oils like butter and a virgin olive oil, because those products are sold as having been minimally processed. So this is why a lot of bakers prefer to use unsalted pure sweet cream butter or extra virgin olive oil, because they actually are less processed. So oil is removed from an oil seed, such as soybeans, sunflower oil, safflower seeds, nuts, and different fruits, for example, like palm fruit and olives. It's sometimes they use pressing, which is the most natural way, but sometimes to speed up the process, they'll add heat and use different solvents, which are then removed before the oil is finished being processed. The solvents are mostly used to break down the oils and extract them quicker and more efficiently by machine so that they can get the maximum yield out of something like soybeans. Hydrogenation makes a liquid a solid, and by doing that, it's less likely to go rancid. Um, it's got better shelf life. Generally, it has very little flavor because all of the impurities have been removed, and it is higher in unhealthy saturated fats and trans fatty acids. But at the same time, there are some benefits to shortening. I may talk badly about shortening, but the reality is that shortening is cheaper than butter. It is easier to handle. It gives you great volume. It gives you great shelf life. It has emulsifiers built in so that it helps retain moisture. So there's all these good things about shortening as well. The downside is that it's less healthy. So liquid oils were previously lightly hydrogenated, which makes them less likely to oxidize and become rancid. It's especially important for oils used for frying. So for deep fat frying, very important in order to get the fat to be stable in the fryer, and it makes for better deep fried goods like French fries. Trans fatty acid free stable oils are now extracted from specially bred oil seeds like soybeans, sunflower, safflower, and so forth. They're lower in polyunsaturated fatty acids, which oxidize slowly and easily. They're high in monounsaturated fatty acids. A lot of shortening companies are trying to get to a point now where they are advertising that they have no trans fatty acids in them. And that's a little bit dishonest because the government regulates them and says that they can have some trans fatty acids in them as long as it's less than 1 gram per serving. So if it's even 0.99 grams per serving, they can list it as 0. So when you're eating something with shortening in it, what you're getting essentially is you are getting some trans fatty acids. It's just a very small amount. And if you have less than a serving, what's listed as a serving, which usually I think is a tablespoon, you'll get a small enough amount where the government says that the company can call it 0. So it's a little bit dishonest. I guess you could say because they're just not telling you the whole truth. So here's fatty acid profiles for different fats and oils. Again, compare regular soybean oil with high oleic soybean oil. And we can see high oleic soybean oil compared to regular old soybean oil. And we'll see that the high oleic has about the same amount of saturated fat, give or take, but a lot more monounsaturated fat than regular soybean oil. And then the polyunsaturated fat in soybean oil, 62%, is a lot higher than the lower amount of polyunsaturated fat in high oleic soybean oil. Which is higher in polyunsaturated fats? Well, it would be the regular soybean oil. And it's probably more healthy for you. But at the same time, high oleic soybean oil is used to make a lot of things that we typically need and typically want in our American diet. High oleic soybean oil, for example, is used to make margarine and a lot of different types of margarine from things like country crock and so forth. And that type of oil creates a better product than regular soybean oil. So that's why it's attractive to a lot of manufacturers. Now, plastic shortening or margarine can be made from partial hydrogenation of a liquid oil where unsaturated fatty acids are converted to saturated ones. So you can see here from the left illustration, we have a partial hydrogenation. So we have a double bond and 2 hydrogens, and we add heat and a nickel catalyst and hydrogen gas, and we get a double saturated or highly saturated solid fat. What that does is it gives you a more solid fat, something that works well in manufacturing environments, but as I say, it's a little less healthy. Plastic shortening or margarine can be made by using a naturally saturated fat like palm oil, and that's becoming more and more common. A lot of Crisco today is made with palm oil, and the reason why is because it's cheaper, but it's also it contains no trans fatty acids. It's more sensitive to changes in temperature, but with proper processing, they're able to get the Crisco to behave like the old Crisco. Old Crisco didn't have nearly as much of the palm oil in it. Instead, it used more domestic oils like soybean oil and canola oil. But instead, they've switched over, and you'll see a lot of these companies using using palm oil instead of some of the more domestic oils. So blending a fully hydrogenated fat with a liquid oil has some of the same features of palm oil and can be also interestified so that it's more plastic. The idea here is they're just trying to customize these fats to make it more attractive to manufacturers. Manufacturers like companies that make mass quantities of, let's say, muffins. You buy muffins from a company rather than making them from scratch. You buy them frozen, pre-made. This company's making 10,000 muffins an hour, and they need fats that perform very reliably. So they get custom fats that work well for their workflow in their factory. So once it's processed to be softened plastic, a shortener is cooled and aerated under controlled conditions to create that smooth, creamy texture that you expect, and the performance that these companies want when they're using these products. Now, butter, I like using butter, but butter is made from heavy cream. It doesn't have any emulsifiers in it. It has a low melting point, and it's rather finicky. You have to really learn how to use butter. Although butter has great flavor, and that's one of the things that I use it for, is for its flavor. Because it is a more natural product and a lot less processed, though there's going to be a little bit different behavior out of the product, so it's less easy to work with. That doesn't scare me away. I think that because it's less easy to work with, I'm willing to live with that if I'm going to get the better flavor and a more natural product. So what are the advantages? Great flavor, superior mouthfeel, fantastic mouthfeel. The only real disadvantages of butter, and I'd say the number one, is the cost. It's very expensive. It's high in saturated fat, so it does contain cholesterol. It has a narrow plastic range, so it's only malleable at a very specific temperature range, whereas shortening is much more malleable at a much wider range of temperatures. And it has a less shelf life, so it really needs to be refrigerated. Unless you're going to be using it up right away, you don't want to leave butter sitting out on the counter for much more than a day or two. What's butter made of? Mostly butter fat that is extracted from cream. European butters typically have higher fat content and lower water content. So our water content here in America is about 16 to 18%. We also have milk solids like proteins and sugars like lactose and some minerals. That lactose helps contribute to good browning, which is something you don't get with shortening. You can also add salt, and air is sometimes added to butter, but generally most butter is pretty solid stuff. I think butter, to me, is a more superior product, but moving on to another fairly natural and fairly less processed fat is lard. Lard was used for a long time, and it's basically just hog fat, just pig fat that's been rendered down and purified. What they do essentially is try to get rid of all the smell and a flavor of meat that is in it, to try to get it to be more neutral. There's several different grades available. It is not kosher, so remember, it's from a pig. So if you're cooking for anybody who's Jewish or Islamic, they cannot have anything with lard in it. But that said, there are restaurants popping up around the nation that use lard proudly, and they have even advertised that their entire menu uses lard as the only fat in their menu. And they've become quite popular for it because people really who grew up on lard, they really like the mouthfeel, they really like the taste. The highest grade of lard is called leaf lard, which surrounds the kidneys in a hog. It's very pure. It's extremely it has an extremely high quality, and there's very little of it on each hog, so it's highly prized for what it is. And you can see this. Here's an old advertisement for lard. They're happy because they eat lard. Other ads that were used for lard. This is about these ads came out about the time when shortening first started making its debut back in the 1930s. They're young, they're in love, they eat lard. Or he's a bouncy little chap because his mom uses lard. When shortening first came out, the lard companies that made lard were very nervous because they thought this meant the end of their industry and the end of their livelihood. So they started to really advertise lard. One disadvantage of lard is that when you're trying to cream sugar and fat together, lard will not cream. So when it comes to making cookies, butter or shortening work much better. Lard is great for a lot of other things, though. It makes a fantastic pie crust. It makes fantastic other products. But lard, they thought at the time in the 1930s that lard it was going to die. It was going to disappear off the face of the earth. But it's still here, and it's still widely used. So what this chart shows is the melting point on a graph. It shows basically going from 0 to up to 100 degrees Fahrenheit, from 50 to 100 degrees Fahrenheit, and how many relative solids are left in the fat at a given temperature. And you can see table margarine, which is made mostly of shortening. The dotted line goes down here, and it still retains some solids all the way up until a little over 100 degrees Fahrenheit. Whereas butter, the solid line drops down, the solids drop down, and by the time it reaches 80 degrees Fahrenheit, most of the solids are gone. By the time it reaches 90, almost no solids are left, so it's almost completely liquid at that point. Margarine essentially is just imitation butter. It's meant to taste like butter, it's meant to act like butter, but it isn't butter. And you can definitely tell if you taste the two side by side. Anybody who says, oh, it tastes just like butter, no, it doesn't. It doesn't taste anything like butter. But it's meant to be an inexpensive substitute for butter. Margarines are widely used in the baking and pastry industry because they are less expensive, and they are made up mostly of vegetable fats, but hydrogenated vegetable fats. And they do add some water, some flavorings, some color, usually beta-carotene as a coloring. And the water content is similar, about 12 to 15% water is used in typical American margarines. And really, one of the main reasons why people buy it is because they've grown accustomed to it, and they like the flavor of it. But it's also less expensive than the real thing. So there's different classifications of margarine. You can see regular table margarine. There's baker's margarine, which is much firmer than what you would find in the store. There's roll-in margarine, which basically is these are slabs of margarine that are made in slabs specifically for bakeries to use to make danishes, puff pastry, and croissants. And it is already made into a rectangular slab so that it makes it easier to jump into production, wrap your dough around it, and start rolling out the margarine to make a laminated dough. And there's specific puff pastry margarine that's meant specifically for puff pastry. It has a much lower water content, and the idea there is that it will create a much better, flakier puff pastry than something like let's say a table margarine, which has a higher water content. So here we are looking at different solid fat contents based on temperature again between puff pastry margarine, which, as you can see, the solids are quite high, even at well over 100 degrees. Baker's margarine, again, much higher solid content than table margarine, which table margarine is like what we would get in the supermarket, and it's designed to act like butter. So it's designed to melt when it's put on toast. It's meant to act like butter. to the average American. But baker's margarine and puff pastry margarine are not meant to be used that way. They're meant to be used for specific purposes in a professional bakery, in a commercial environment. So they're designed to have that higher solid fat content at a higher temperature, which will give you better performance when you're using it for large quantities of making puff pastry or croissants or danishes. Now, one of the main big differences between other types of solid fats from butter. Shortening, obviously, made of 100% fat. There's only fat in it. There's no water. There's no milk solids. It's made specifically to be 100% fat. And that makes for a very good pie crust because you don't have water in there. It's originally developed as a replacement for lard, but it's very good for a lot of things. And the reason why is because it is 100% fat and it has almost no flavor, which means it doesn't alter the flavor of the food. That's a really good thing, especially when you want something that's extremely neutral. So there's all-purpose shortening. It contains very little to no emulsifiers. It may contain an anti-foaming agent, and the idea there is that so it won't get foamy when it's used in a fryer. So when you're trying to, let's say, make your own French fries at home, it won't foam up. So this diethyl polysiloxane is commonly added for this purpose. It's very workable and pliable over a wide temperature range. Really good for creaming, for making cookies, pie dough, biscuits. It's really very useful stuff. This is your basic Crisco. Then there's high ratio plastic shortening. Now this is something we use in the bakery called Sweetex. Sweetex contains added emulsifiers, so mono and diglycerides are added specifically to allow it to absorb and attach and bond better to moisture and to liquids. This helps get air incorporated into the mixture and makes better cake icings. But it also makes it so that a cake batter will it'll allow the cake batter to absorb more liquid, thereby giving you a more moist cake and better shelf life. It's not meant for use in frying or flaky pie dough. It's really more meant to be used to make cakes and make icings. When you have typical, let's say Duncan Hines, buttercream or icing, frosting that you find in the supermarket, mostly it's made with this kind of shortening, that high ratio plastic shortening that is higher in mono and diglycerides, but also more hydrogenated than average shortening. And then there's high ratio liquid shortening. This is typically used a lot in cakes and baking as well. This has a little bit less hydrogenation, high levels of emulsifiers, so it really creates a very high volume, very moist cake, very moist products. It's really used a lot in the commercial world, especially in factory baking environments. They buy it by the truckload. So what do these emulsifiers do? They really help, as I say, to stabilize fat and oil droplets with liquids. And they do that through these emulsifiers. The emulsifiers have, part of them are oil attractive and part of them are water attractive. And that helps to make the two play nice together. Here's an illustration showing an oil droplet with emulsifiers with their oil attractive tails connected to it. And when you have that situation, then the oil won't separate out from the liquid. It'll stay in suspension and stay stable. A good example of a natural emulsifier is lecithin, which you find in egg yolks, and it's used pretty much for a lot of different types of emulsions. But we find one of the more common ones is mayonnaise. Mayonnaise is a very stable emulsion. It will stay as mayonnaise for days and days and days in the refrigerator, and does just fine. Will not separate, and the reason why is because it has so much natural emulsifiers in it. So oil, also 100% fat, no added water, high in poly and monounsaturated fats. You can find liquid oils from a number of different sources in the plant world, and they all have, as we remember from the charts before, that they have different compositions. Olive oil is the most expensive of all oils used in the bake shop, generally refined as light or unrefined virgin or extra virgin olive oils. These oils are highly prized oils. They do have a fairly strong flavor, and they're used mostly in savory applications, but it's a very, as oils go, a very healthy oil. So what do oils do? Oils provide tenderness, as I mentioned before. They shorten gluten and make the product easier to bite through and make things softer, help retain that tenderness. And that's something that we like a lot. We like soft breads, we like soft products. Fat is a very, very important part of that. It provides flakiness in pastries because you can separate dough from fat. What you get essentially is flakes. You get layers. And those layers create flakiness, something that's very, very attractive and very highly prized in baked goods. So here's a good example of flakiness versus not so flaky. That flakiness is very desired in a lot of products. It assists in leavening because if you have fat separating layers of dough, it provides gaps and spaces upon melting for steam and other leavening gases to expand into. So this is where you get those flaky pastries. Some products have no yeast and have no baking powder or baking soda in them. All they have is fat and dough. And if that's the case, you're relying on steam and trapped air to do the leavening. And the fat helps with that process. So here's a good example of that where we see like the cross-section of a croissant after it's been baked, or a Danish would look like this as well. Nice open cavities where there's air and nice flakes. It helps to contribute to moistness. Now don't mistake fat for moisture. It's not liquid. It's not water. It's just, it gives the perception of moisture. But more important is that when emulsifiers are present, the moisture of actual water is bonding with the liquid in an emulsion, and that's what really helps to hold that moisture in. So the fat provides just the feeling of moisture in a product. Now, when something is overloaded with fat, it can just be oily, and people may say, "Oh, it's really moist," but it's not. It's just oily. But a balance of oil and liquid, especially with the aid of an emulsifier, gives you real moisture and the feeling of tenderness and the perception of moisture from the moderate amount of fat that's in the product. Because it helps retain moisture, it helps prevent staling. Moisture has a hard time getting out of the product. So when there's enough fat in a product, it'll help reduce the amount of evaporation that takes place. And that evaporation is what we call retrogradation, where starches start to release moisture off over time after baking. If you lose too much of that moisture, you end up with something that is perceptibly stale. And there's a point at which all products are stale to a certain point, but there's a point at which you will not eat it anymore because it's too stale. And what's happened there is that the starch has let go of the moisture. The fat, although tried to prevent it and reduce the amount of retrogradation, it's still eventually, most baked products will get stale. Fats contribute flavor. A lot of different fats have flavor of their own, but they also absorb flavors from around the fat. So basically, they can help to carry flavor. And it's like Emeril Lagasse used to say on television. He used to always say that fat equals flavor. Well, he's right in that both fat is flavorful, but also it helps carry flavor. And there's a lot of other functions that fats have in baked products. They contribute color. They provide fine crumb to baked goods, so it helps to make the product again, give a better perception of tenderness. It adds creaminess to sauces, custards, and confections. Even though there's not as much fat in it, let's say a custard, it's there and it helps create a creaminess and a good mouthfeel. It helps conduct heat. It provides bulk and substance to icings. After all, a lot of our icings and frostings are made primarily of fat. It promotes smoothness in confections. It blends flavors, masking off flavors, acts as a release agent, releasing agent in that it helps keep things from sticking to the pan. And increase softness and extensibility of doughs. Things like bread dough become much easier to work with and much softer and easier to handle if they have a little bit of fat in them. Thinning out melted chocolate. After all, chocolate is almost all fat. There's a lot of fat in chocolate. And it's almost all cocoa butter. But After all, that's what makes chocolate so special. And then it increases spread in cookies. When fats melt in the oven, that's what helps make cookie dough spread out and make a cookie. Otherwise, they would remain as balls of dough and they'd be hard as hockey pucks. So fats must be protected though, because they do absorb smells, they do absorb flavors from around them. So if you store, let's say, some butter next to an open bucket of onions in your walk-in refrigerator, your butter will start to smell like onions. So they will absorb odors. They do spoil. Eventually, fats will become rancid, and usually you know it right away, especially certain fats will start to go rancid fairly quickly. So exposure to light, heat, air, and other things around them can cause fats to go rancid. I notice almonds, other nuts that have high fat content will start to go rancid fairly quickly, and what they do is they smell and taste like wet cardboard. Not a pleasant thing. So when you substitute butter or margarine for shortening, remember that the butter or margarine have some water in them. So you have to make a calculation because shortening has no water in it. So if butter or margarine, let's say, has about 80% fat and the rest of it is a mixture of water and sugars and other things, if we're going to replace that with shortening, we need to account for that. So we would reduce, for a pound of shortening, you would use, let's say, more butter to get the amount of fat that you would to replace the shortening, but you would reduce the liquids overall by about 20%. And what that would do is that would approximate the amount of fat and the amount of liquid from the original recipe, now using butter instead of shortening. And if you're going to go backwards and substitute shortening for butter, you would say, okay, well, I had a pound of butter in the recipe. I'm going to multiply that times 80%, get 12.75 ounces of shortening, and increase the liquids in the rest of the recipe by 3¼ ounces. The idea there is that it's going to help to approximate the amount of fat. We're going to go into the lab next, and when we go into the lab, we're going to be experimenting with pie dough. We're not going to be filling the pie dough with anything. We're just going to be making the dough itself and baking it off and looking at how different fats affect pie dough. We're going to be able to be using shortening, margarine. We're going to be able to use real butter and lard, and we're going to be able to see the difference in how these different fats react with a basic dough, a very basic dough like pie dough, and compare them side by side, both with color, texture, flavor, the general flakiness, the general volume. We can look at all of these things in pie dough and be able to compare them side by side. As you make one of them, you're going to choose what fat you'd like to use, and we're going to compare yours with other people in class who perhaps used a different fat. And that way we'll be able to know a bit more about these fats and a bit more about also just with pie dough. Which fat would you prefer to use in your pie dough as opposed to another fat? Would you prefer to use lard in your pie dough as opposed to, let's say, shortening? And why? Why would you choose to use that as a pastry chef or as a baker to use for a certain product instead of the other? Would one be more superior? We also should consider cost as well. And obviously some fats cost more than others. So depending on what you can charge for a particular product, let's say an apple pie, you may be forced to use a less expensive fat to make a product more affordable for your customer. Anyway, we'll see you in the lab tomorrow, and make sure to watch the videos, and we'll see you tomorrow in uniform with your masks.